Hello again, my name is Samuel Breslin, and this is, I believe, the fourth video in this series of LTM lectures that I'm creating. So to start this one off, I want to make a few corrections from our last video and change the schematic symbol. So the first, really the only correction to make is here. This N reset pin has an internal pull-up resistor and a weak internal pull-up resistor. So we do not need this here. And instead, we're going to add a 100 nanofarad capacitor to the bottom here. And go ahead and add ground, or we can just do this. And this is going to act almost as a filter so you don't get sort of a bunch of spontaneous resets. I always forget which capacitor I'm on. 13. Capacitor 13. Okay. We're also going to I'm going to copy over the schematic symbol from the SolarGators library as opposed to the manufacturer part search. Like I said, it's no different. The actual footprint that we'll be designing around in the PCB design is the exact same. I just prefer the look of that schematic symbol. So STM32 L496. This one. It's just a slightly different schematic symbol that I prefer. So we'll go ahead and drop this in. And this is a slightly different schematic symbol, so we're going to go ahead and remove and move. So we still have all of our ground pins over here, power pins over here, and reset is just moved up here. I don't think we'll use serial wire output. Oh, and I forget which pin that was all on. Let's see, we've got serial wire output on PB3. We'll go ahead and add that back. And clock is on 1314. This is on 13 and 14. Go ahead and move all of this. I just like the schematic symbol a little better because it is a little smaller. Okay, that's a bit of an issue. Again, we're double clicking on these net labels to change the orientation of, or change where it snaps to the wire. Okay, we have N reset. And then we have our STM OK and error LED indicators. Go here, and we have boot 0, which also is going to move to the other side. Okay. All right. We are all set up with our new schematic symbol. Okay. The only other thing I'm going to do is add a new schematic, and I'm going to rename this to be connectors, and I am going to cut all of this stuff, Control X, and add it over here, as this is a connector. And I'll name this J1, I believe. J1 should be fine. Okay, and we'll leave that there. Okay, so we have our MCU, we have our error LEDs, which we'll place up here. Okay, perfect. Okay, so in this video, depending on how long that it runs, I am going to focus on two things. One is going to be adding a memory chip to the schematic, as well as adding a sensor known as a inertial measurement unit. So we're going to start with the inertial measurement unit, and we'll see if we have time for the other for the memory chip. So the inertial measurement I'm using is the MPU 6050. Manufacturer part search. MPU 6050. Right click, place. Okay. So now I could just show you how this is all connected up, but like I said, I want to teach you guys how to design these schematics and not just exactly what to do, so that you can go off and find, say you want to add a different type of sensor, you can teach yourself how to do that. We're going to start with the easy pins. NC stands for no connect, so we're going to go ahead and hit P, and then go to our directives, generic no ERC, just telling Altium that it's not a mistake that we left these pins unconnected, and tell it that these pins are going to be left unconnected. Okay, VDD, that's just going to be our power, which is going to be 3.3 volts. So we'll place a power pin and call that plus 3V3. Go ahead and make that seen and connect it up to power. Ground, that's pretty self-explanatory too. We'll go ahead and wire that straight to ground. EP is going to be a pad. I'm going to show you what it looks like on here. So here's our schematic, our footprint. EP is this center pad, and that's just going to be connected to ground. So we'll go back to our MCU. So that is also going to be connected to ground. We'll leave those for now. Okay, clock in. All right. Now, before I go any farther, I want to talk a little bit about how this sensor here is going to connect up to the microcontroller here. Let me rename that. 1, UA 1, U2, about how this is going to communicate with the microcontroller. And to do that, we're going to use a protocol called I2C, or integrated circuit. And that is just another serial digital protocol. So we're going to go ahead, let's choose which pins on here we're going to use for I2C. And again, the best way to do that would be to go here to CubeMX or CubeIDE and use the this graphical interface that they have to look at where your I2C ports are and which one you want to use. For this, I'm just going to go ahead and take a look at my previous design, my reference design, and I'm using PB10 and PB11. I don't know what that's doing out there. PB10 and PB11. Okay, so PB10 and PB11. I'm going to go ahead and add two net labels, PN2. Obviously, I will rename them in a moment. This is going to be I squared C underscore SCL and I2C underscore SDA. So that stands for I squared C serial data and I squared C serial clock. So I'm going to get into this in the embedded lectures in the difference between asynchronous and synchronous, but essentially this is a clock pulse that tells the peripheral device here, the sensor, how often it should sample this data line. Okay, so now we can go ahead and wire I squared C directly to the SCL and SDA pins here. So I'm going to place our net labels, tab to change the justification, and we're going to wire those up. I2C underscore SCL, right? And I squared C underscore SDA. Great. Okay, now unfortunately there's slightly more to do with this communication. So I squared C, depending on what kind of speeds you're using and things like that, requires pull-up resistors. So that is, and we discussed what the pull-up resistors were in previous videos. And yeah, so I used 4.7K. Let's go to components, and we're going to add a 4.7K resistor right next to each other. One is going to pull up the SDA, and one is going to pull up SCL. And we're going to make this resistor 7, 8, 11. R9. Okay, yep, R9. And this will be R10. And these are both going to go to power. So I'm going to go ahead and copy and paste that from somewhere. Beautiful. And all. I'm going to go ahead and move all this outward. Okay, there is our pull-up resistors and I squared C lines. That's all great. So now we need a little bit more information on how to wire up the rest of this stuff. So we're going to go to the components data sheet. There we go. Get rid of all these other tabs here. I'll just go ahead and okay, so here's our MPU 6050. Allow all. You gotta go ahead and find the data sheet. GitHub is always a good website for finding data sheets. Sorry, not GitHub, DigiKey. GitHub is not a great website for finding data sheets. And most of these data sheets are going to have an application schematic or an example application schematic, and that's going to be plenty good for our purposes. Okay, so here we go. Here's two typical operating circuits. We are going to be looking at, well, they're pretty much the same, but let's go ahead. We're going to start with pin 1 or clock in. Okay, so pin 1 or clock in is an optional external reference clock input, and it says to connect it to ground if unused. And I'm pretty sure we are not going to be using that. I'll make sure. Yeah, so clock in is going to be connected to ground. Um, so I'm going to place ground over here, and it's going to be a weird placement, but it will make sense. It'll make sense in a moment. Next, we're going to go to pin number 2. Sorry. Okay, pin number 2. That is going to be, oh, not internally connected. Maybe use, okay, so 2, 3, 4, and 5 are not connected. Okay, so let's move to pin 6. Pin 6 is the I2C master serial data, which we already connected. Pin 7 is serial clock, which we already connected. Pin 8, SPI chip select, which we're not going to be using because we're using I2C and not SPI. So according to this application schematic, I believe this is our I2C one. Sorry, we were on pin 8. I believe we can go ahead and wire that high, but I'll make sure. Sorry, it's always tough to remember. Yeah, okay. Pin 8 can just be wired high, as I said. So we're going to go ahead and place a power port over here. Pin 8 is just going to be wired up to that. Okay, we're flying through pins. Pin 9, AD0, I2C least significant bit, or SPI serial data output. Okay, so we're using I2C, and this pin represents our least significant bit. So again, part of the way that I2C works is it's based on addresses. So if you can have multiple peripheral devices or slave devices on one I2C bus, and so each of those devices is going to have an address. Now, say you wanted to have, and usually most of that address is sort of hard-coded into the hardware of the sensor. And so if you wanted, say, multiple of that sensor on the same bus, say you wanted 2 of these sensors, you would need some way of configuring the I2C address. And this pin allows you to do that. So if you tie this pin to ground, it's going to make the least significant bit of the I2C slave address 0, where if you tie it high, it's going to make it 1. So that's our pin 9, and we're going to go ahead and tie that to ground. So again, this pin just gets tied straight to ground. Okay, pin 10, regulator filter capacitor connection. So this is just asking for a filter capacitor on pin, we were working on pin 10. So it's specifying or showing the example of 0.1 microfarads or 100 nanofarads. So let's go ahead and connect that up. And I believe that's connected to ground. So I'm going to copy that. And again, I know it looks a little weird the way I'm doing it, but it's all sort of thought out. I believe this is going to be capacitor 16, maybe? Is it? Did I get that right in the first try? No. 14? 13? Okay, 14. Capacitor 14. Connected to ground. Okay, and then we're also going to want to give it a net label so that when we're routing it, we know what's what. We'll delete that for now. So PN tab to change the justification and place it right on the corner, and we'll call it reg out. Beautiful. Okay, there's pin 10. Let's move on to pin 11. Pin 11, FreeSync, connect to ground if unused. We're not going to be using frame synchronization, so we're going to connect to ground. Awesome. So FreeSync is over here, and just connect to ground. Awesome. Okay, pin 12 is int or interrupt. So that is going to, you can configure the IMU sensor here to use this interrupt pin in different ways, right? So one of the most common ways is going to be if, say, data is ready here on the sensor will drive this pin to be high, which might trigger an interrupt over here on the microcontroller. So we're going to go ahead and just give that a net label called IMU int. It's already there for me. IMU int, and I'm going to go ahead and connect it to a pin on the microcontroller. I'm going to do pin number PB12. PN IMU int. Awesome. Okay, PB12 IMU int. Okay, so now we're on pin 13, which was VDD. We can go to pin 14, which was no connect, 15, 16, 17, no connect. Pin 18 is ground. Pin 19 is reserved V. What does that mean? Let's go find out. 19 and 20 are reserved, do not connect. Sorry, pin 19 and 21 are reserved, do not connect. So we'll go ahead and do that. PN that. Okay, do not connect. Pin 20, we skipped that. Okay, pin 20 is the charge pump capacitor connection. And 22 is also do not connect. So for the charge pump capacitor connection on pin 20, it looks like we want a 2.2 nanofarad capacitor connecting to ground. So let's go to components, 2.2 nanofarad. Okay, so it looks like we don't have a 2.2 nanofarad capacitor in our SoliGators components library. So I am just going to capacitors. Okay, so I'm going to go to our manufacturer part search and get a 2.2 nanofarad 0402 capacitor. We'll just go with this one for now. I just want one with a similar schematic symbol to what we have. That looks good enough to me. Actually, you know what? I'm going to continue to use our SoliGators parts library, and I am just going to have to make sure. Okay, yeah, I'm going to have to make sure I'm going to use a 22 nanofarad capacitor, and I'm just going to have to make sure that when I go to actually assign these parts, when we're ordering it, I instead use a 2.2 nanofarad capacitor. And that's going to be on CP out right here. Okay, let me think. How did I do it over here? I made it look nice and pretty over here. Okay, 3.3 volts, kind of hidden, and that's all the way on the outside. This is going to need a little bit more room to breathe. Let's see if we can just change this label. Okay, beautiful, 2.2 nanofarad capacitor. It's obviously it won't match up with the part number, but we're going to go ahead and assign it to a different part anyway. And that's going to be C15, which I'm going to connect to ground. And then as you saw in that other photo, we're going to connect this V-logic pin to ground through a 100 nanofarad capacitor. Also, again, sort of a filtering capacitor. Okay, and then we're also going to add net labels for CP out. PN, CP out. Awesome. All right, so now we're up to pin 21, 22, our clock output. Okay, pin 22, reserved out, do not connect. Pin 23, squared C serial clock. Interesting. 324. Okay. Yep. Yep. 2324 is our squared C serial clock. What did we do with? And this is going to be unused. Effective. No. And then what were we doing with 6 and 7? Did I miss those? 6 and 7. I squared C master serial clock for connecting to external sensors. We're not going to be using that. So P, no ERC. Awesome. Let me make sure that agrees with my example here, and that all looks good other than a 100 nanofarad capacitor filtering our power supply. So we'll go ahead and add that. Capacitor 16. Capacitor 17. Okay. That all looks pretty good to me. How long are we running? We are 27 minutes. So yeah, I'm going to stop this recording. But thank you. And I'll leave it off on